Welcome to the High Voltage AI Podcast.
Glad to be here.
We're incredibly glad you've joined us for what promises to be a really insightful week.
Hi.
This is actually the first installment of a special series we've put together. It's meticulously crafted for you electric utility engineers, and it's all featured in the High Voltage AI newsletter on Substack. Throughout this week, we're really going to be peeling back the layers on some critical technologies and concepts. You know, stuff that's shaping the future of our grids.
Yeah, it's moving fast.
It really is.
Yeah.
So today we're embarking on a deep dive into the virtual power plant revolution, from concept to grid-scale reality. You know, the North American grid is facing just unprecedented challenges. Feels like it anyway.
Absolutely. Peak demand is surging.
Exactly. Surging peak demand. We've got a steady march of traditional generation assets heading into retirement.
Yeah, the old plants are aging out.
And those transmission corridors, they're already strained to their absolute limits in many places. I think most of us remember that fateful winter, right, 2021, when the Texas grid was pushed way past its breaking point.
Oh, yeah. That was a wake-up call.
It really was. And that moment vividly highlighted this urgent, almost desperate need for new capacity, flexible capacity, and capacity that can be deployed fast. So what if the answer isn't, another huge monolithic power plant? What if it's an innovative kind of unseen solution, something already existing in like 1 million homes and businesses hiding in plain sight?
Well, that solution, in essence, is the virtual power plant, the VPP. And it's so critical to grasp this. A VPP is not a physical power plant, and not in the way we traditionally think about it, with smokestacks and turbines. Instead, it represents a really profound shift, a fundamental change in grid architecture itself. We're moving, kind of slowly but surely, away from relying only on those big, centralized, often mechanical assets, towards a future that's built more on decentralized resources, intelligent resources, and importantly, software-defined resources. It's like a digital transformation hitting the physical grid.
A digital transformation for the grid. I like that. And that really sets our mission for today, doesn't it? We're going to unpack what virtual power plants truly are, how they fundamentally differ from those traditional power plants we've all worked with for decades, and crucially, why getting a deep understanding of VPPs is, well, it's rapidly becoming a foundational competency, a core skill for every power systems engineer out there. This isn't just theory anymore.
No, it's practical. It's about the skills you'll need, probably starting now, but definitely tomorrow.
Okay, so let's pull back the curtain and let's unpack this. When we talk about a virtual power plant, what are we really talking about? What's its anatomy, so to speak?
Okay, so at its core, a virtual power plant is it's a sophisticated system, usually cloud-based, and it aggregates distributed energy resources, DERs. You'll hear that acronym a lot. These DERs are then orchestrated, managed by highly sophisticated software. Think of it like this. You gather and coordinate thousands, maybe even millions, of these small or medium-sized energy resources. And when you do that collectively, they provide the same reliability, the same economic value, and often actually more flexibility than a single big traditional power plant. It's basically a decentralized network that acts like one single unified thing.
Okay, DERs, distributed energy resources. What kind of things fall into that category?
Right. So these DERs, they're a remarkably diverse mix of devices, really. You find them everywhere. Homes, businesses, industrial sites, even EVs, electric vehicles. We usually put them into two main buckets, sort of. First, you've got your demand-side resources, sometimes called load flexibility. These are devices that fundamentally they consume energy, right? Mm-hmm. But they have this ability to flexibly change how or when they consume it, usually responding to grid signals.
Like smart thermostats.
Exactly. Smart thermostats controlling your heating, ventilation, air conditioning systems. That's a classic example. But also things like grid interactive water heaters, heating water when power is cheap or abundant. Smart appliances. Electric vehicle chargers that can maybe pause charging during peak hours or shift it to overnight. Even controllable loads in commercial buildings or industrial plants that can trim their usage for a bit. The really revolutionary idea here with demand-side flexibility is that for grid operators, avoiding consumption, creating what some people call negawatts, is often just as valuable as generating new power, sometimes more valuable.
And no fuel costs or emissions, right?
Right, precisely. No fuel, no emissions. And a VPP can, collectively cut the load on the grid by tens, maybe even hundreds of megawatts just by orchestrating these flexible loads. It's quite powerful.
Okay, so that's demand side. Controlling usage. What's the other category?
The other main category is supply side resources. And this covers generation and storage devices. So these are assets that can either, well, generate electricity or store it, and then inject that power back into the grid when it's needed.
Okay, like what?
Think residential rooftop solar arrays,
Uh,
or behind-the-meter battery storage systems, maybe in your garage, maybe in a business. Also, electric vehicles that are capable of vehicle-to-grid power export, V2G. That means the car's battery can actually send power back to the grid.
okay.
Yeah, it's still emerging tech mostly, but huge potential. And even sometimes traditional backup generators can be part of a VTP if they can be dispatched strategically.
Okay, that sounds, coordinating thousands, maybe millions of these totally different devices. Solar panels, car chargers, thermostats, batteries. How do you possibly make them act like one coherent power plant? Yeah. What's the central nervous system here?
Yeah, that's exactly where the real innovation is, and also the immense challenge, frankly. The brain of the VPP, if you will, is its central control system. And in modern systems, this almost always leverages artificial intelligence, AI and machine learning. This advanced platform, it's continuously watching grid conditions, dynamic conditions in real time. It's forecasting load patterns, forecasting generation patterns, often hours, maybe even days ahead. And then based on those forecasts and what the grid needs right now, it sends out precise commands to those thousands of aggregated URs. It does this to meet very specific grid needs. Maybe it's reducing peak demand to, prevent issues. Maybe it's providing super fast frequency regulation to keep things stable. Or maybe it's soaking up extra renewable generation when it's really sunny or windy.
And how does it talk to all these devices?
Good question. This whole thing relies on really robust, secure two-way data exchange.
Great.
Bidirectional. So you'll often have remote control units installed maybe at the site of each asset or built into the device itself. They send real-time data back to the central platform, and they receive dispatch instructions. This communication usually uses standardized secure protocols, things like IEC 608705104, which is pretty common for power system telecontrol. Needs to be secure.
That really highlights just the complexity and sophistication involved here. It sounds like a pretty profound convergence, doesn't it? Two very different worlds colliding, the physical grid and the digital realm.
It absolutely is. We're witnessing really nothing less than a profound convergence. The energy sector and the information technology sector coming together in a way we haven't seen before. Think about it. The reliability of a VPP now depends just as much on the integrity of its data streams.
The data?
Yeah. And the performance of its algorithms, as it does on the physical state of the actual devices, the DRs themselves. So this isn't just about learning some new software tools. It fundamentally shifts what grid reliability even means.
Yep.
It's no longer just about physical infrastructure being resilient. It's equally about the resilience and, critically, the security of the data and the algorithms running the show. And as a result, grid operations are rapidly turning into a massive big data challenge. It demands continuous analysis, rapid response. This means that utility engineering departments, they increasingly need to cultivate deep expertise in areas like cloud computing, AI, machine learning, telecommunications security.
Skills maybe they didn't focus on as much before.
Exactly. It really blurs those traditional lines, between power systems engineering and software engineering. It demands this new kind of hybrid skill set for the future.
That's a huge mindset shift, definitely.
Yeah.
Especially for an industry historically focused on, the physical stuff, wires and transformers.
Okay, so it's clear how VPPs operate internally, sort of the nuts and bolts. But how does this revolutionary VPP model really stack up against, say, a traditional power plant, like a natural gas peaker plant we might use for peak loads? Where do the fundamental differences lie?
Yeah, the differences are pretty stark. And they really signal a true paradigm shift in how we think about grid resources, how we deploy them, how we operate them. Let's kind of break down the key distinctions. First, think about the mechanism, how they actually deliver power. A traditional plant, coal, nuclear, natural gas, it burns fuel, or splits atoms, right, to generate new electrons. A VPP, though, it primarily makes power available in two main ways, either by conserving or shifting energy use that's already happening. That's the demand side, the megawatts we talked about.
Right. Or by dispatching energy that was previously stored or generated. That's the supply side assets like batteries or solar. So it's much more about optimization and orchestration, not necessarily just raw generation from scratch.
Okay. Different mechanism. What else?
Next up, location and ownership. This is a big one. A traditional plant is a single centralized facility, often covers acres of land, typically owned by a utility or maybe an independent power producer. A VPP, however, is a geographically distributed network. spread out. We're talking potentially thousands, maybe millions of individual components. And often these are owned by individual customers, homeowners, businesses, or maybe third parties who aggregate them.
So not utility-owned necessarily.
Often not, or only partially. This decentralization, it's not just a logistical difference. It's a fundamental rethinking of how we even get grid resources.
Okay, makes sense.
Then there's deployment speed. Think about building a new gas peaker plant. Or any large-scale generation, really. It can take years, many years sometimes. Permitting, design, construction.
Oh yeah, the regulatory hurdles alone.
Exactly. Environmental assessments, the actual physical build. It takes time. A VPP, though, because it cleverly leverages existing customer assets or ones that are going to be installed anyway, it can often be planned and deployed much faster, sometimes as little as, say, 6 to 12 months.
6 to 12 months versus potentially years.
Yeah. That rapid deployment is incredibly valuable, especially when you need to address urgent capacity needs or react to grid changes quickly. It's just a totally different timescale compared to traditional long-term planning.
Wow. Okay, speed is a big one. What else?
Scalability, another major difference and a huge plus for VPPs. A traditional plant is a big monolithic investment, right? You build it, it has a fixed capacity, that's it. If demand grows past that, well, you might need to build another whole plant.
Right. Big chunks of capacity.
Big chunks. Virtual power plants, on the other hand, are modular. You can scale them incrementally. Just enroll more DERs, more smart thermostats, more batteries, more EVs as they come online. This reduces the capital risk quite a bit. You're not making one giant bet up front. And it lets the resource kind of grow organically with the grid's needs, almost like a living system adapting over time.
That's fascinating. Modular and organic growth. Okay, one more.
Yes, and it's critical. Resilience. A big centralized plant, it represents a single point of failure. Think about it. A localized equipment issue, maybe a severe cyber attack on its operational technology network. You know, the control systems running the plant itself, ideally kept separate, air-gapped.
The OT network, yeah.
Right. Or just an extreme weather event hitting that one spot. Any of those could take the entire facility offline, and that impacts a huge service area. A VPP, because it's distributed all over the place, is inherently more resilient. If individual DERs fail, one smart water heater goes offline, one battery has an issue. The impact on the overall aggregate capacity is negligible, usually tiny.
Because the others just keep going.
Exactly. If one water heater is down, the other, 99,999 keep performing their function. That distributed nature builds in resilience.
That really drives home just how different this VPP model is. It does feel like, as you said, a genuine democratization of grid services.
Yeah.
Where consumers become active participants, maybe even get compensated, instead of just being passive ratepayers.
It absolutely does. It unlocks a powerful new resource, empowers consumers.
You also mentioned new risks earlier.
Yeah.
Especially around that massive cybersecurity challenge you touched on. Are utilities or the VPP operators, are they really prepared for that kind of distributed risk? What are the biggest hurdles there?
Yeah, that's the flip side of the coin, isn't it? This democratization is fantastic, but it absolutely introduces a completely new and frankly incredibly complex risk profile, especially cyber. You nailed a key point there. Think back to the traditional plant. It usually has, a hardened physical perimeter fence, guards maybe, and largely an air-gapped OT network designed for pretty robust security, physical, and cyber. It's like a fortress, or tries to be,
right.
A VPP. By contrast, it has potentially thousands, hundreds of thousands, maybe millions of endpoints, and these endpoints are often consumer-grade devices, your smart thermostat, your EV charger, located in homes, in businesses, and crucially, they're connected often via public communication networks, home Wi-Fi, cellular networks.
Not dedicated secure lines necessarily.
Often not. So this means the VPP's cybersecurity attack surface is just exponentially larger and way more porous than a traditional plant's OT network. Imagine you're a system operator. You're relying on, say, a 1 gigawatt VPP for critical capacity during a peak event. Now you have to worry about the security posture, the vulnerabilities, the potential attack vectors of millions of individual disparate devices out there, owned by different people, running different software.
That sounds like a nightmare to manage.
It's a monumental challenge. It really goes far beyond the traditional OT security frameworks, which were designed for a much smaller, more controlled set of utility-owned assets. The biggest hurdles right now, things like standardizing security protocols across all these diverse device manufacturers, developing real-time threat detection that works across such a massive distributed network, and even just figuring out clear lines of responsibility for cybersecurity. Who's responsible when something goes wrong? The utility, the VPP aggregator, the device maker. the homeowner.
Yeah, that's complicated.
Very. So that democratization of grid services, it's incredibly beneficial, huge potential, but it's inextricably linked to this distribution of cybersecurity risk. It's a trade-off, and it requires really careful ongoing management.
Okay, so given all these transformative aspects, attack the risks, the benefits, what does this all mean? Why should you, our listener, as a modern power systems engineer, why should you care deeply about VPPs? What's the practical impact on, your daily work and the grid you manage?
Right. VPPs are way more than just some novel tech trend. They're becoming a versatile, almost essential tool, capable of providing a whole spectrum of services that directly tackle the grid's most pressing needs. And their value proposition, it stretches all the way from the bulk power system managing big generation imbalances, stuff like that, right down to the local distribution feeders, maybe solving localized congestion on a specific circuit.
So top to bottom usefulness.
Exactly. One of the most common immediate applications you see is peak shaving and load following. VPPs can significantly cut system demand during those really expensive, often carbon-intensive peak hours. Think about a blazing hot summer afternoon in Texas or California or anywhere really, air conditioners running full blast. VPPs can intelligently coordinate thousands of thermostats to pre-cool slightly, or maybe dispatch batteries to inject power, reducing that overall peak load. This helps grid operators maintain reliability, sure, but just as importantly, it can help defer or even avoid the need for really costly investments in new power plants or big transmission and distribution upgrades.
Which saves everyone money in the long run.
Exactly. It's often a highly efficient, faster, and definitely more environmentally friendly alternative to building massive new infrastructure.
Okay, peak shaving, load following, what else can they do?
Well, beyond just managing demand levels, the more sophisticated VPPs can provide critical ancillary services. These are the services that maintain overall grid stability, kind of like the grid's shock absorbers. This includes things like frequency regulation, where the VPP makes rapid, small adjustments to power injection or withdrawal, maybe within milliseconds, just to keep the grid's frequency stable right around 60 hertz.
Keeping everything in balance.
Precisely. And they can also provide operating reserves, which means having capacity ready to respond super quickly if there's an unexpected outage, like a large power plant tripping offline, or a sudden surge in demand. A VPP can potentially step in almost instantaneously to fill that gap.
That's incredibly valuable for reliability.
Huge. And finally, another key role is renewable integration. VPPs are turning out to be an incredibly powerful tool for managing the inherent variability of wind and solar power.
Because the sun doesn't always shine, the wind doesn't always blow.
Exactly. So during times when you have too much renewable energy, maybe a really windy, sunny day, and low-demand VPPs can act like a sponge. They can absorb that excess clean energy by charging batteries, maybe preheating water in those grid interactive water heaters, or even pre-cooling buildings a bit more. Then later, when the renewable output drops the sunsets, the wind dies down. The VPP can discharge that stored energy from the batteries or reduce load from the flexible devices, effectively balancing the grid and ensuring a continuous power supply.
So they smooth out the bumps from renewables.
They really do, which significantly enhances the grid's ability to actually host more clean energy without becoming unstable.
That flexibility across all these areas, peak shaving, ancillary services, renewable integration, it's genuinely striking. These capabilities, taken together, they deliver pretty profound system-wide benefits, don't they?
Yeah.
I mean, we're talking enhanced reliability and resilience for the whole grid. Improved affordability for customers because you're avoiding some of those massive infrastructure builds, speeding up decarbonization goals, and enabling more widespread electrification, more EVs, more heat pumps.
All of the above.
It really does sound like a cornerstone technology for the grid of the future.
I truly believe it is a cornerstone. And that's why, for the modern power systems engineer listening today, understanding VPPs, figuring out how to harness their full capabilities, it's really no longer just an academic exercise or something for the R&D department. It is becoming maybe the critical competency needed to effectively build, operate, and maintain the grid we need for the future. A grid that's dynamic, resilient, and sustainable. The whole landscape is shifting, pretty dramatically actually, and VPPs are right there at the epicenter of that shift.
And this was just scratching the surface. Remember, this was just the first part of our week-long series, designed specifically to deep dive into the topics that matter most to you, the electric utility engineers. So be sure to tune in tomorrow. We'll be talking about inside the Texas VPP and ERCOT's groundbreaking pilot. We'll actually explore a real-world case study there.
Yeah, see how it works in practice.
Exactly. And as you think about today's deep dive, here's maybe a provocative thought to chew on. How will this increasing reliance on software-defined grid assets, like VPPs, how will that fundamentally reshape the career path and maybe the required skill sets for utility engineers in the future? Something to ponder. If you'd like to leave feedback or have any questions, feel free to reach out to our producer, Julia Squai, on LinkedIn.